Okay, let's get started. Okay, so in our last lecture, we finished the proof of the channel coding theorem, right? And then we focus on the converse part. And then we start talking about the feedback capacity. So which basically means that, so if we can fit the output back, and use that information to do the encoding, and then, what we can achieve, right? Okay, so for the channel coding theorem, so for the converse part, so we need to remember the steps, okay? So we introduce in total 5 steps there, okay? And you can see today and in the future lectures. So these 5 steps are pretty general, okay? For most of our proof, we're gonna use these 5 steps, right? So. And as you can see today, for some steps, right, we may need other techniques, but in general, those steps are there, okay? And one of the most important steps is to use Funnels inequality, okay? So we need to be pay more attention on that. Okay, and then we talk a little bit on the zero error code, okay? For the zero, we finished talking, did we? Yeah, we talk about zero error code. Yeah, for zero error code, so basically it means that the error of each message has to be 0. Okay, so it cannot be epsilon, right? And then we give an example that, the noise typewriter example. And you can see that for this example, then it is possible to design a zero error code, okay? But the problem is not that trivial, right? So basically it means it's similar to the, asymptotic small error case. We need to let the length of the code becomes large. And we show an example that if we use length 1 and length 2, you can see there's a clear gain in terms of the capacity if we increase the length of the code. Okay, so we can pack more information for each channel use, basically. And obviously, the capacity of the zero error code is less than or equal to the capacity with the symptotic small error code. Okay, so yeah, that's the zero error code. And then we introduce the feedback capacity. So basically, as we said before, so for feedback capacity or for feedback channel, so now you need to consider this encoding function, right? So basically, we have the message m, and then we need to use all the feedback information up to I-1, right, to do the encoding, right? So we assume here there's a 1-step delayed feedback, right? So assume the feedback is not immediate, right? At this time slot, we have the feedback from the last time slot. Okay, therefore, so the encoding function look like this, right? We use the message and all the feedback information. Okay, and then, so everything else would be the same as before, okay? And here we still consider a block code, right? So we have this RN code, okay? And then capacity of feedback channel is defined on all the achievable R, and then we take the supremum of it. Okay, so that's the feedback channel capacity. And so we introduce a theorem to show you that, okay, so for a DMC channel, so the feedback capacity will be the same as the channel capacity without feedback. Okay, so this is a rather surprising result, but we have some condition, right? We have some discussion that will be talked in the next slide. Yeah, but here we have a few remarks here. So obviously, the capacity of the feedback channel should be larger than or equal to C, right? We show that they're actually equal, right? But if we don't know the theorem, so this should be bigger than or equal to that, right? We just say, okay, bigger than is not possible, only equal. Okay, in order to show this theorem, the only thing we need to show is that, okay, so this has to hold. Okay, and then we can show the theorem, right? So you can see this is basically the converse part, right? So we do not need to show the achievability, right? Why is that? Because we show the achievability for the channel without feedback, right? So we can have the option to not use the feedback, right? Without feedback, we can achieve that. So that's the achievability can be used for the feedback channel as well, right? Therefore, we do not need to show that the achievability or the direct part for the feedback channel, right? Yes?
Was for the first inequality, like the C of like the feedback greater than just like the normal channel? channel capacity. Is that just true because like we should be getting less error if we have like feedback?
Oh, this is true simply because now, so this is an encoding function, right? We use M and we use all the feedback, right? If we do not, therefore, we have more information to use, right? Therefore, if we do not use those informations from y1 to yi minus 1, then we can achieve the channel capacity without feedback, right? That's the meaning of the first inequality. Okay, so if we use less information, and then we can achieve, we can do pretty much the same thing as this. Now we have more information, therefore, so we can achieve definitely at least equal, right? So this bigger than or equal to means at least equal, right? But we show, okay, so bigger than is not possible. Only equality is possible. Is that clear? Okay, so that's the logic. So therefore, we only need to show the converse part of that, right? So which we're going to show that today. Okay, and here are a few discussions. So yeah, this result is a little bit misleading. It doesn't mean it's not correct. It's totally correct. But it's a little bit misleading because it doesn't mean that the feedback is not useful, right? So we cannot translate the theorem into this sentence. Okay, you just say that, okay, when n goes to infinity, right? Remember, so how we define the error probability, right? When this n has to go to infinity, and then the error goes to 0, and then what's the maximum rate r? Okay, so this supremum basically means that n goes to infinity, right? So yeah, that's the mathematical meaning of it, right? But it doesn't mean, it only means that, okay, in this symptotic range, the capacity is the same. Okay, it doesn't tell you anything else. For example, so we show one example in our last lecture. We show a BEC channel with ARQ. Okay, that with feedback, we can design a much simpler code to achieve the channel capacity. Right, the code is very, very simple, right? So therefore, with the feedback, at least, we can save on complexity. Okay, so in practice, we always use the ARQ. Okay, so we use feedback explicitly in practice, right? It doesn't mean feedback is not useful. Just asymptotically, the capacity is the same, okay? And another condition here is that it has to be DMC channel. The channel has to have no memory, right? So if the channel has memory, then it's another story. So feedback can probably increase your channel capacity. Okay, yes? Yeah, now we're considering DMC channel, right? This channel with memory basically means that the DMC condition does not hold. Is that clear? Okay, and another thing is that, so if we consider a multi-user channel, meaning that, let's say, if we have a multiple access channel, let's say we have 2 transmitters, like your phones, and 1 receiver, like the Wi-Fi access point, right? If 2 phones transmit signal to the Wi-Fi access point at the same time, okay, then this is called like multi-user channel. It's not point-to-point anymore. Or vice versa, the broadcast channel, right? For example, like the Wi-Fi access point will communicate with 2 phones or 2 laptops at the same time. So this is called broadcast channel. Okay, so we're not going to cover those channel capacity in our class. It's it's a more advanced topic. But for those kind of channel, we can show that feedback can indeed increase the channel capacity. Okay, can indeed increase the channel capacity significantly, right? So basically, yeah, that is, you'll need to be more careful on that as well. Okay, so even for memoryless channel. Okay, and we covered that, so we can achieve a lower coding complexity. Okay, and today, so we're going to show how we can improve the converse of the channel with the feedback first. Today is our lecture number 31. Today, first we'll talk about the feedback capacity. And then we'll talk about joint source channel coding. Okay, so joint source channel coding basically means that, so before when we or yeah, we're going to introduce a theorem here. So it's called source channel separation coding theorem. Separation theorem. So basically, the reason we talk about this is that, so one of the reasons is that when we prove the channel capacity, we have a very important assumption there, right? Which is the source has to be uniformly distributed. Yeah, what do we mean by that? It basically means that the source is a compressed source. It achieved the entropy already, right? If it's uniformly distributed, then it achieves entropy, right? It's a compressed source. It's compressed already. Okay, so now a natural question may arise, right? So in practice, when we have a source information, maybe like a voice message or like some videos or images, right? So, okay, so the raw messages may not be compressed, right? If we want to transmit those messages over a channel, what should we do? Okay, so this will help us to solve this problem, right? So one obvious option is that, okay, we compress it and then transmit, right? Or can we do something else, right? For example, can we just transmit it directly, without compression? Or, if the channel has some special property, right? For example, if the channel, when we transmit a 1, the channel does not make any mistake, but when we transmit a 0, it may make some mistake. And then, should we, when we do the source coding, right, will that impact our coding? It is, right? We should transmit 1 more, right? Something like that, right? So then, in this case, we may need to consider more because the channel may impact our source coding. Okay, so that's why we need to study that. And then, we may not have time, but the next topic will be chapter 8. Okay, where we're going to the continuous area. Okay, so now everything we talk about is discrete, right? So everything is discrete, and we haven't touched anything continuous in our class, right? Because the definition of entropy is for discrete random variable, right? If it's continuous random variable, for example, if like Gaussian distribution, we don't know how to compute the entropy. We don't even know what is the definition of the entropy, right? But in practice, obviously, we have lots of continuous random variable, right? For example, everything transmitted over the air is analog, meaning it's continuous, right? So for continuous random variable, what should we do? Okay, and then, so we're going to focus on that quite a bit, okay, in this class. Okay, so let's start for the first topic, feedback capacity. Okay, so now we're going to prove of the converse. So this is more or less an exercise on what we have learned before, right? So again, so here we assume that the message M is uniformly distributed over from 1 to up to 2 power nr. Okay, and then, so I hope you can write together with me, right? Let's see, so where we got stuck, right? Because, so now the idea is pretty much the same as before, exactly the same. So the first step is that, okay, so we write this rate. We need to connect the rate to what? Entropy, right? The first step, okay? Because it's uniform, then we have an equality sign. If it's not uniform, then this guy has to be larger than or equal to that, which is not good, not what we want. We want the upper bound, okay? Second step, okay, the same. So we basically want to create a term of mutual information, right? There's only one way to do that. You just write down this, and then add this back. Okay, the second step, exactly same as before, right? The third step is to use funnel, right? So this guy, by using funnel, we can show this guy is less than or equal to this nr. Okay, so therefore, so now we have this guy plus 1 plus nr p bar and a bar here. It's average error probability, right? The reason we can use average here is that we have a uniform distribution, right? The average basically means that we can make an error. Okay, great. Are we good so far? Okay, we have 3 steps, right? So what's next step? What is step 4?
Data processing.
Exactly, data processing, right? So now, can we do data processing? Right? Data processing basically means that, so we have Markov chain from m to xn to yn, right? So this follow a Markov chain, okay? Then we can do a data processing. But now, can we do that? Can we use data processing? No, we cannot, right? The reason is that, so this y will impact here, right? So the coding is a function of m and the y up to, whatever. Right? It's not a Markov chain anymore, so we cannot use data processing, okay? Cannot use data processing inequality anymore. Okay, so very bad. We cannot use data processing anymore. Then what should we do? Okay, so here you see that it diverges, right? But the step is still the same. Why we want to use data processing? Because we want to create a term of I, x, n, and yn, or y, x, h, I of x and y, right? We still want to do that, right? The step doesn't change, right? But the technique has to be changed, okay? So we cannot use data processing, then we use something else, okay? So what we're going to do is as follows. So it is also a very standard approach, right? Because we want to deal with that term, right? So if we cannot use data processing, we just write it out, right, and see what we can use, right? So let's see what we can use, right? So be careful here. So we write this in terms of hm minus hm given y already, right? So normally we cannot write this equal to that because we used that before. Okay, we have to write it in another way. Okay, so I think that's pretty intuitive. Otherwise, we're doing in loops, right? We have to write this in this way. Okay. Okay, so expand mutual information in this way. Okay, so not so bad, right? The first term is easy, right? So we have bound the first term before, right? We just use, write this separately, and then it's automatically an upper bound. Okay, but so we need to deal with that term, right? And so this is not difficult to do, right? Because now we have a joint entropy. There's only one way to deal with joint entropy, so which is the chain rule, right? So just write out the chain rule here. Okay, so after writing using the chain rule, so we have yi given yi minus 1 and n, right? So this is the chain rule, definition of the chain rule. Okay, very good. And then what do we do? What do we need to do? Remember, so what we need, is mutual information between x and y, right? So here we have a y already. So then we need hy given x, this kind of thing, right? Our goal is to have hy given x. But here we don't have any x. Therefore, so we need to somehow create x. How can we create x? Right, so this is very important, and we always do that, okay? So in order to create x, we need to observe this very carefully, right? What is that? M is the message. I minus 1 is what? The feedback. Therefore, from here, we know x. Does that make sense? Right, so from here, we can get xi, right? So that's the encoding function, right? It basically means that, so we have, from here to xi is a deterministic function, okay? Does that make sense? Therefore, what we can get here is that we can simply add xi here for free, right? Because xi is a function of this too, right? Adding xi, we do not know any more information, right? Okay, very good. Yes?
Is there a reason why we don't just drop the yi minus 1 in the m term?
Very good. That's excellent. There's no reason to not drop it. We're going to drop it in the next step. Very good. Yeah, because it's a Markov chain, right? So we get from here to x, and then y is determined by xi only, right? We just drop it. Okay, so now I think it's pretty clear, right? So we have seen that before, right? So then we just have upper bound on this. Oh, and so it's not equal. Just be careful. Although, even though it's a DMC, it doesn't mean yi are independent, right? Because x can be independent, can be dependent, right? So just be careful on that. So we have upper bound here. And then this equals to the mutual information xi, yi, and this will be less than or equal to nc. And then we'll finish the proof, okay? Yeah, and then the next step would be exactly the same as before, so I don't need to repeat. Okay, is that clear? Okay, very good. Yeah, you can see here, right, the technique here we use is this technique, right? So, I mean, this technique is pretty standard. We use that all the time. But, for a more complicated problem, there's no standard technique. We need to try all different approaches to manipulate. Okay, yes?
Can you get to the, yxi is deterministic for yi minus 1 and then?
Oh, this is from the definition,
Oh, it's just
right? For example, let's say here. So x equals to m from y1 to I minus 1, right? So yeah, we use this information and all the feedback to have our code word. Okay, is that clear?
Yeah.
Okay, very good. So let's continue. Next topic is source channel separation theorem, or joint source channel coding. Okay, so now we want to consider a most general case, right? So we consider a general source, which we may not compress it first. Okay, so what we consider here is a stationary ergodic source. That is the most general source we considered in the compression part in chapter 5. And also in chapter what? There's 11, or we have a later chapter. We also cover something on that, right? So, so here, let's say we wish to transmit a stationary ergodic. The reason we want to use stationary and ergodic is that we want to have entropy rate, right? Otherwise, we cannot have entropy rate. Information source, so that's Vi, okay, over finite alphabet V, okay, and also over a DMC channel, okay, X, P, X, and Y, P, Y given X, and Y. Okay, so we'll consider a ergodic source transmit over a DMC channel, right? So remember here, so this is very important, DMC and the stationary ergodic source, that's very important, okay? So now the system diagram is as follows. So now we have a VK here, right? K is the total number of symbols in the message, okay? So now VK may not be uniformly distributed. Right before, for channel coding theorem, we assume the source is uniformly distributed, but now we relax that condition, so that it may not be uniformly distributed. Okay, then therefore we cannot, relate that, relate the rate to the entropy anymore. So we're going to see what else we can do. Okay, and then we have an encoder in general, and then from the encoder we have our coded information xnvk, right? K is the length of our source message, and n is the length of our code. Okay, so we pass that through a channel py given x, and then we have a yn, and then we pass that with a decoder, right? And then we have vk hat. Okay, and you can see that we do not have a source coding, and we don't have a channel coding separately, right? We only have one encoder here. Okay, so this basically means that we have a joint source channel code. Okay, or we say it's a joint source channel coding. So it's a combination of the source coding and the channel coding. Okay, here you can see that we have a K there and we have an N there, right? So basically now we define this compression ratio tau equals to N over K. Okay, so basically it means that it's the number of channel uses per source symbol, right? So that's the channel uses per source symbol. Okay, and then we fix it. Okay, that's the parameter we care about. Okay, that makes sense? So we fix that parameter. Okay, so n could go to infinity and k could go to infinity, but the ratio is fixed. Does that make sense? Okay, and then we want this number to be as small as possible. Right. Okay, so that's basically that's the basic setup. Okay, so now let's write down, so what is our problem definition, right? So now we need to define what is the encoding function, what is the decoding function, and what is the error probability that we care about. Okay, and yeah, let's see how we can define those. So now you should be pretty familiar with the information theoretic language, right? So basically, so first let's define what is the encoding and decoding function. Okay. So now we'll consider a joint source channel code. Okay. For this setup is defined by, okay, first we have an encoding function. Okay, we use phi to represent it. So phi is from the vk to xn. Okay, and a decoding function. We use psi to denote that. So this is from yn to vk. Okay. Okay, so basically the function can be written as this. So vk hat will just equals to psi yn, right? So it's a deterministic function. Okay, and clearly here xn, we can write that as phi vk. Okay. Okay, similar as before, the average error probability So that is defined as this. So now we have two parameters, or you can write that as tau, right? Kn. So that equals to the probability that Vk and Vk hat, which is phi yn. Oh, yeah. Let me write it more. Yeah, I'll write it in the next lines. So this equals to the probability that Vk and phi yn, so they're not equal. Okay, so that's the average probability, right? Y here is a random variable. Okay, very good. So, and next, we need to define the achievability, or right? So here, because we want to transmit something, right? So we say transmissible in this case. We say that the source is transmissible, over the DMC with compression ratio tau. So if there exists a sequence of codes such that k goes to infinity. Okay, therefore n also goes to infinity, right? And n equals to k times tau. Okay. So tau is fixed. Remember that. Okay, such that the average error probability goes to 0, right? So don't need to care about the maximum error probability, right? Because this will imply the maximum error probability. We can only do the error. We only need to do the average error probability, and then we're good. We're good. Okay, great. So this is the problem setup, and you should be pretty familiar with this kind of language, right? We have done this many times. Okay. So next, let's see. Okay, so let's go back. So if you're the designer, how can you design it? Can you use what you have learned so far to design a code here? Okay, I think the most intuitive design would to use the separate source and channel coding, right? Because in chapter 5, we learned the source coding. In chapter 7, we learned channel coding, right? So now we want to do both source and channel coding, right? So one intuitive way to do that is we do the source coding first, and then we do the channel coding, right? So basically, it's like what we are doing in practice, right? We won't have a source, we won't have a voice, then we're going to compress it first, right? And then transmit. Okay, when we transmit, we do a channel coding. So now we use the LDPC code, before we use the turbo code, and so on. Okay. So basically, intuitively, what we should do is as follows. If we have a source, we do a source coding first. Okay, and then we have the message M, right? So which is the symbol we use when we talk about channel coding. And then we do a channel coding on M. Okay, and then we have X, so which is our transmitted code word. Okay, then we pass that through a channel, Y given X. It's a DMC channel. Okay, and then at the receiver side, we receive a YN here. Okay, so when we do the decoding, so we can do two steps as well, right? We need to do the channel decoding first. Okay, and then we have an estimate of our message M hat. And then when you do a source decoding. And then we have our VK hat. And then we're done, right? That makes sense. It's pretty intuitive, right? So yeah, that's an approach that okay, we can do, right? So yeah, let's consider a simple case, right? Let's say, okay, what if the source is memoryless? It's not with memory, right? So let's roughly compute what is the requirement on tau, okay? So how good we can do with tau, right? So basically, let's say, okay, if Vk is equal to k times hv, right? So we just simplify this a little bit to get some intuition, okay? And then, so this guy is the entropy of the source message, right? And if we, let's say, if we do the best of the best, right? So we design a source and can achieve the entropy, then this will equal to the entropy of M, right? Let's see, M is the best source code we can find. It can achieve the entropy, okay? And meanwhile, so this is the rate, right? So this is also the NR in this case because we're already uniform, okay? And from the channel coding theorem, we show that so this guy is less than or equal to NC, which is the channel capacity, right? Okay, and now from here, what we can get, right? We can see, so this guy will be less than this guy, right? So the entropy of our source will be less than or equal to N times the channel capacity. Does that make sense? So if that holds, then we can transmit. Equivalently, if we divide it by k on both sides, we can see the entropy of the source has to be less than or equal to tau times c. Okay? Does that make sense? Okay, if that happens, then we can say that Vk can be recovered with high probability. Okay? Does that make sense? Or it is too trivial? Yeah, seems pretty trivial, right? Because, okay, so this is a source entropy, right? And so we're going to transmit it using n-channel uses. Of course, this has to be less than the n times channel capacity because we have n-channel uses, right? It is very, very straightforward. Do you agree? Okay. And so basically, so this is the formula that we can get. Okay. And overall, so this scheme, is like what we are using today, right? So this basically means that, so we first perform source coding, and then channel coding. So this is called separated source channel coding. Okay, so if it's separated, then as long as this condition is satisfied, then we can do the transmission without any error or with an arbitrary small error. Okay, so next question is that, okay, so whether the joint source channel coding is better than separated source channel coding. Okay, so our question is that whether joint source channel coding is better than separated source channel coding. Okay? What do you think? So if, when we do the source coding, by jointly consider the channel property, right? For example, if the channel cannot transmit a 0, then we never send a 0, right? It doesn't make a lot of sense, right? If the channel can transmit, for example, 0, it can transmit 1, 2, 3, but cannot transmit 0, and if the source has a 0, then we don't want to use 0 symbol, right? So intuitively, there is some gain to consider the channel when we do the coding, right? Consider joint. It seems to make sense, right? Okay. What do you think? Yeah, do you think we're gonna have any gain if we do the joint source channel coding?
I would think so.
I think so. Yeah. Any different opinions? Yeah, for point-to-point DMC, lots of weird things happening, right? It turns out that, in terms of capacity, there's no gain. Okay, obviously, when we consider complexity or not DMC channel, there may be gain. Okay, but for DMC channel, there's no gain. Okay, so that's why, that's one of the reasons that we use this separate scheme today, right? For all the system, we do not use. Not for all most of the system, we do not use the joint source channel coding, right? We just compress the source first without knowing the channel and then transmit, right? So the advantage of it is very clear, right? So we can separate the design, right? Because if we design source coding based on this kind of channel, if the channel we do not apply, for this channel, then we have to change the code, right? Design would be complicated. It seems complicated, right? But if we do them separately, it's universal, right? We can compress the source first and then transmit that over whatever channel, as long as we can use the efficient channel code, right? So this theorem, basically tells us that, you can do this. It may be more complex, but if you compress your source first and then use a good channel code to transmit, you do not have any loss in terms of channel capacity, in terms of tau, the compression ratio. Does that make sense? Okay, so this is a fairly interesting and strong result. So now let's and so basically this is the constraint, right? As long as this constraint is satisfied, and then we can do separate source channel coding. Okay, and then or vice versa, the separate source channel coding can achieve that. Okay, which is the best you can do. Okay, so let's write down the theorem. Source channel coding theorem. A stationary ergodic source Vi, okay, with Vi is in V, is transmissible over the DMC channel X Py given X and Y with compression ratio tau if H of V, so this is the entropy rate, okay, is less than tau times C. Okay, so this guy is the entropy rate. And this C is the channel capacity. If we look at the first glance, right, it is a very non-trivial result, right? Because this is the entropy rate, and so this is the channel capacity, but it's the channel capacity only if the source is uniformly distributed, right? So it's a pretty non-trivial result. Okay, and conversely, if this guy is bigger than this guy, then the source is not transmissible over the channel. Okay, So this is a joint source channel coding theorem. So I have one remark here, right? Although we say, okay, in terms of capacity, right, or in terms of this, whether it's transmissible or not, so it's not helpful for joint source channel coding. But in terms of complexity, joint source channel coding can indeed help, okay, in some cases. When coding complexity is considered, the joint source channel coding may have advantages. Okay, very good. So any questions so far? Okay, so now let's take a look at the proof, right? We're not going to show you the whole proof, but just a ballpark of the proof. Okay, so first let's see the achievability. Okay, how we can, do the achievability? It should be pretty straightforward, right? Because I tell you that, the separation does not have any, loss. Therefore, we just to use the separated source channel code. Okay, so first we do a source coding. And then with the rate of what? K, HV plus epsilon for any small epsilon. So this is the rate for the source coding. And then we know this is achievable, right? And then we do a channel code. The channel coding rate is what? Right, it's C minus epsilon, right? Okay, and the argument will be pretty much the same as before. The source coding, you can just pick the typicality coding we introduced before. For the channel coding, we just use random coding, right? Source coding, we just do the typicality. And channel coding, do the random coding. Right, just combine them, right? And we can show that if this guy bigger than this guy, the source rate, okay, and then we're okay. Okay, and then so you can feel that, then we're okay. Otherwise, it's not okay, right? So this is basically the achievability part. Okay. Do a typicality for source coding and random for channel coding, right? So, or if it's not extremely clear, then in the middle step, we may add this, right? So this is less than NR is bigger than or equal to that, and then we're good. Okay. Yeah, this R is the rate of the channel coding rate. Okay. Okay, so this is achievability, right? So you can feel the proof, hopefully. Okay, and for the converse, okay, actually the idea is exactly the same as before. Okay, so basically what we do is that, so now we cannot have this M, right? Because for the converse it has to be general. We cannot have M, okay? But look at this. Look at this. So this is what we want, right? So basically, what we can do here is as follows. So basically, we start from K times HV here. Okay, and from here, we can get this. Right, K times the entropy rate will be less than that. Okay, and this is basically the key step here, right? And then, so we can write this, use the idea before. This is the first step, and here now is the second step. So we need to create the mutual information. Okay, because this is a recovered message, right? So basically, this is what we do. No. Okay, and then the same as before, for the first part, we get a mutual information between VK and VK hat. And then for this part, we just use the funnel, right? So that will be less than or equal to 1 plus P bar in and the log VK. Yeah. Okay, so now this is the second step. Okay, then we're almost done, right? The third step is what? Now we have this, right? The third step is to have something related to x and y, right? So now what we can do is that use the data processing, right? So here we have this Markov chain. We have vk from xn from yn to vk hat, right? So we can use data processing to have this plus 1 plus this log vk. Okay, very good. And then we're done, right? So we know this is less than n times c plus 1 plus, here for this guy. So that's k times p nk. Yeah, we need to write nk here, so not only n. Here's a typo, nk. Oh no. Okay, log, very good, p nk, n times log v. Okay, and then we're done, right? So basically now we have this guy is less than this guy, so we have this guy is less than this plus 1 over k plus this. Okay, so now we can k goes to infinity. So this guy will go to 0 when k goes to infinity, and this arrow has to go to 0, right? And then we're done. Okay, and then we can show that. So this guy is less than or equal to this guy, or should be only less. Because we have k and this term here, right? And then we're done. So this is a proof. You can see that the proof here again, so is identical as before. It's exactly the same. Okay, so the very key step here, the only difference from this step to what we covered before is probably the first step here, right? So this inequality is coming from the proof of the entropy rate, right? So we can show this guy is smaller than that. Okay, so we can, and so this is the first step. But again, you can see the first step is pretty much the same, right? But we may need a different inequality there. Okay, I think that'll be it. And then we're now officially finished chapter 7. So you should be able to do all your homework. Okay, so we're going to talk about chapter 8 in the next class. Okay, bye.